In this video of the fundamental of electrical circuits, we will be talking about voltage divider. As the name implies, voltage divider is a case where you need to divide the voltage down. For example, you could have a 10 volt, but your system needs a 5 volt, and you need to bring that 10 volt down to 5 volts so you can use it in your system. So in a typical, the simplest voltage divider you can have is you have a voltage that is given, voltage source, let's say we have a 10 volts here as an example, and the user is asking, or your system really needs only 5 volts. So the question is, how do you get that 10 volt to the 5 volts? As you know, based on the earlier videos, is that every time you put a resistor in the path, certain amount of voltage will be lost, and so all we have to do is put a resistor in the way, another resistor here, and in this case, if let's say call this one R1, and let's call this one R2. So if they are giving us an input voltage Vin of 10 volts, and they're asking for an output voltage that is 5 volts, all we have to do is figure out what value of R1 and R2 we need. Hopefully this is simple enough that you can take a look at it, say, hey, if they have 5 volts here and they want another 5 volts here, then I simply have to, all I have to do is make sure R1 is equal to R2, and this way I'm going to see only 5 volts here. So this is kind of, we can just look at it and kind of make a determination, but we also can, let's say if it wasn't that simple, let's say for a more involved example, someone will say, okay, use voltage divider to get 4 volt from a 20 volt supply. Again, based on what we just talked about, we have a source that is 20 volt. That's what they've given us, and we know in order for us to be able to get a smaller voltage, in this case we want our V out here, this is our supply voltage or in voltage they have given us. We want the V out to be 4 volts. The question is, how do we do that? We just got to select the right R1 so it can consume whatever is left over from 20, and we got to select an R2 so it gives us that. So the question is, what do we know? For one thing, we know it's V out is equal to 4 volts. Now, we can think back of all the analysis tools that we've learned so far, and we can use any of them. KVL and KCL are the very general ones. Anytime I can use KCL or KVL, my tendency is to use those. So in this case, we notice that we can use KVL by calling this I, going around the loop. So if I were to do a KVL at I1, I will have minus 20 plus R1I plus R2I equal to 0. So in this case, you will see that this will also give me another equation to help me. If I V out, we know V out is equal to R2 times I, so I can come here and say, okay, I times R2 is equal to 4 volts. Hopefully you'll see that I have 2 equations at this point, but I have 3 variables. In the cases where you have more variable than you have equation, it means that you're going to end up with lots and lots of answers that would satisfy your equation. So if we solve this, from here we can find I is equal to 4 over R2, and I can take that and replace it on the top equation, which gives me minus 20 plus R1 I actually we're going to replace I with 4 over R2 plus R2 4 over R2. This and this cancels, which what I'll have if I clean this up, 4 and 20 becomes minus 16, goes to the other side. So I've got minus 16, which becomes positive 16 when it goes to the other side. And then I have 4 R1 over R2. So if cancel 4, we'll find out that R1 has to be equal to 4 R2. Okay? If I satisfy this relationship, I will get 4 volts out there, which means for every, if the current is 1 amp, I will have 4 volts here, and I will have 1 volt here. So we can actually, so that's interesting. At this point, I is very dependent on the sum of R1 plus R2. So for example, if we were to see somebody just want to build this, therefore we got to give them a value. So I'm going to use this equation and say, okay, I'm going to have R1, R2 value, and what are the possible value of R1 and R2 I can select to get the right answer? We said the only relationship that has to be true is this relationship. Therefore, I can select 1 ohm, or I can, if I select 1 ohm here for R2, I will have, I should have selected the other way, but this will work as well. The R2 means it's going to be 1/4 of ohm. Or I could say, no, I want to select this one to be 1 mega ohm, which means this is going to be 250 kilo ohm, or 1/4 of a mega ohm. So why would I select this versus that? Now, it gets kind of interesting because if I select this, notice the power consumption. Let's take a look at the power consumption in this circuit. Power is equal to V, which is 20 volts, right? Power is equal to V squared over R, total R. So in this case, it will be 20 volts, which is from here to here, divided by R1 plus R2. So in this case, it'll be 20 squared divided by 1.25, which is 1 plus 1/4. As you can, this is approximately 300 and some watts that you have. This is a very large number. That's enough to heat up a small room. In this particular case, if you come down here, then the power is going to be V squared over R. But in this case, you're going to have 20 squared divided 1.25 times 10 to the 6, which means in this case is going to be 20 squared, which is 400 over 1.25 milliwatts. So here you're looking at 20 squared over 1.25 milliwatts. Actually microwatts. So it's 1,000,000 times smaller in power consumption. So now you say, why don't we go the biggest resistor that is out there and use that? And so the plus is that the larger resistor require less power, smaller resistor require larger power, and of course we always want to minimize the power. So why wouldn't we go with the largest resistor that is out there? Here is the problem. Let's say I use the large resistor and I build the circuit. Here's my circuit, and I decided to use 1 mega ohm here. I'm sorry, I think I got R1 is 1 mega ohm, and then R2 is 0.25 mega ohm. Great. So now you've got your 4 volt here. What if the reason you build this is because there's gonna be a device, a load, which, let's say this is a charger for your for your phone. Now you're going to come and connect your phone to this device. Now let's see what happens. Let's say your phone, it's a 1 kilo ohm device. So if I do that, then I have to look at this as I have to combine these two resistors together from earlier videos. You know, you can combine this by basically 1 over 250 plus 1 over 1 over the whole thing. And if when you combine this, this is approximately 1 kilo ohms. Now, if you go back and redo the voltage divider equation that we worked out, in this particular case, your V out, the V across this, it's going to be very, very small. It's going to be roughly 20 millivolts. That's not what you were looking for. You were looking for 4. You got 20 millivolts. So like engineering, like every engineering problem, this is again a trade-off. If you go with the very, very small resistor, you get very, very high power consumption. But when you load it, when you attach your device to this thing, this is called a loaded voltage divider, your voltage doesn't change because 1 ohm or a quarter ohm in parallel with 1000 is still going to be a quarter ohm, so you're going to get the right voltage. But in the case where you went with a very large resistor and you got a very small power, now when you load it, things fall apart. Okay, so let's go back and summarize the voltage divider. Anytime you have a voltage divider, the easiest thing to do is to go ahead and do a KVL on it and solve it. Now, you're going to end up, because regardless of what voltage divider you're working on, you're going to end up with more variables than equation, which means you're going to have lots of solution, and you have to decide. You have to pick either one of the resistors to figure out the other resistor, and you have a choice of either optimizing for power or optimizing so the voltage output doesn't change when you load it. And usually, you know, you have to trade off, find the optimum place where you can have both the right power consumption, so your battery or your power cost will not go too high, and then also have so that the V out doesn't change too much when you load it with a new resistor. So that brings us to the end of the voltage divider video.